This is the second section on the hypothesis testing chapter, and this is something called finding critical values. Now you'll remember that in the first section, a hypothesis test is basically about, has something gone wrong, has something changed from what we expect it to be, and the way that we decide is that we have something called a significance level. And our significance level is like the cutoff point. It's the level of probability, or the percentage at which we say, right, something's not right here. So if I go from 0% to 100% like this, I might decide, right, anything below 5% is odd. It might be 5%, it might be 10%, 1%. These are common percentages. So anything below 5%, we say we would reject H0, there's something wrong. Anything above 5%, we'll say it's fine. And often what we need to do is to work out what value of X we can go to before we start saying things are wrong. Okay, so in other words, at what value of the thing that we observe do we begin to say something's not right? I'll explain it another way. So let's say that I don't know. Let's go back to our soup example again, and I took a sample of 50 people. Let's make it 20 people that bought soup, and I've got a new improved recipe. Now let's say that 20 people, a sample of 20 people that came into a cafe, so in a cafe, and out of those 20 people that came in, let's say 5 bought soup. Yeah, and it may be I'm deciding, right, okay, is 5 people coming to buy soup, does that show that the percentage of people that have bought soup has changed from before? Well, quite often it's useful to know at what number of people buying soup means that something has changed. So is it 5 people? Is it 4 people? Is it 3 people? Does that show that it's decreased, or is it 6, 7, 8, 9 people? So at what number do I decide things have changed? In other words, at what observed value, which is what we call X, which is the test statistics, that's the thing that we observe, yeah, the thing that you count. At what number do I say things are changing? In other words, at what number, for example, so let's call this little x, actually let's use a different letter, A. At what value of A is this dropping below the significance level, dropping below, I'll just put SL, the significance level, or of what value of X, I'll call that A, again let's use a different letter, B, where this drops below the significance level, dropping below the significance level. So we're looking at the questions a slightly different way. We're actually working out what value of X are we going to say we're going to reject H0. At what value of the thing that we observe am I going to say, you know what, things have changed, things are different to what they should be. And we call this, these values that we have here, we call them the critical values. Critical values. So let's say, for example, if I had a critical value of, when I was doing, let's say I was doing something like this, let's say I had a critical value of 4. Then actually what I would say, I would talk about a critical region of being, if I observe anything that's less than 4. something's wrong. Let's say in something like this, I had a critical value of 10. Then what I would say is if I observe anything more than 10, there's something wrong. I would talk about that being my critical region. So once we've got the critical value, we can then find what we call the critical region. So again, this can sometimes be tricky to get your head around. The maths isn't actually difficult, but just understanding what you're doing and why you're doing it is the hard part. Okay, so here's a table of values. This is in the back of the book, and it's also in the formula booklet. Now you can get bits of the table up on your calculator, but it's too fiddly. It's easier to use the tables, and we're going to be using the tables to find the critical region. So let's say, for example, that our significance level was, let's go for 10%. So let's add a 10% significance level. Yeah, and I had a probability of 30%. And I'm looking for the observed values, the values of X that drop below 10%. Okay, so I'm going to be looking at this part of the table. So this part of the table here. Okay, so let's have a look at the first line. So when my observed value is 0, it's about 2.82%. When my observed value is 1, it's 14.93%. Now at the 10% significance level, my critical value would be X equals 0. And my critical region would be anytime I observe anything less than 0. What if I change my significance level to 20%? And I'm looking for at what values, when I'm looking for a decrease in something, a decrease in a percentage, am I going to think there's something suspicious? So again, using the table again, if I have a look at this first value again, this is less than 10%. This is less than 10%. Okay, now then it jumps to over 20%. Sorry, I said 10%, I meant 20%. So what does this mean? This means that if I observe anything less than or equal to 1, I'm suspicious. So we talk about our critical region, or my critical value should be X equals 1. It's my critical value, and my critical region would be less than or equal to 1. Now sometimes we need to find a critical region at the other end, and a critical values at the other end. Now there's some writing here at the side. We're going to use this to help us, and it's useful to understand what these tables, or how we use the tables backwards. So for example, let's take this value here, yeah, in the probability 25% column. Now what does this actually mean? Well, that is the probability that X is less than or equal to 4, okay, which is that one. But, so let's write it down, 0.9219, but it also means 1 minus that value is the probability of X greater than or equal to 5. So 1 minus that same value is the same as the probability that X is greater than or equal to 5. Now why is that? Because the probability that X is greater than or equal to 5 is equal to 1 minus the probability that X is less than or equal to 4. Yeah? And the same with another value. If I took this value let's go for this one here. So this is for 35% probability of success. Now, working from the top of the table down, this means the probability that x is less than or equal to 7, and that's 0.9952. But it also means 1 minus that number, 0.9952, is equal to the probability that x is greater than or equal to 8. Now, why is that? Because the probability that x is greater than or equal to 8 is 1 minus the probability that x is less than or equal to 7. Yeah, so make sure you understand what it means when you work this way up the table from the top. It's easy to work this way and say, well, it's less than or equal to something, but we need to be able to interpret what it means the other way. Okay, a single observation is taken from a binomial distribution. The observation is used to test the null hypothesis that the probability is 35% against the alternate hypothesis that the probability has increased from 35%. Using 5% level of significance, find the critical region for this test. Right, so the first thing we need to do is we're only going to be looking at the part of the table which is for 35%. So we are going to be looking at this part of the table only. So we can ignore the rest. We're only looking at that part of the table. So why not just scrub it out? I'm not going to scrub out too much because there's other stuff we want to see. So that's all we're interested in. Okay, forget everything else. And it says that we need to use a 5% level of significance to find a critical region for this test. Now, it's important to note that this says an increase from 35%. This means we're trying to find a value of x where, let's write this down. So we're trying to find a value of x, or let's call it a, where greater than that is less than, let's write it out fully, is less than 5%, where what observed value is dropping below 5%. Now, we know that the way that we work this out is we do 1 minus the sort of number below it. So the easiest way is to try and find values, because we're doing 1 minus. Little tip, we're going to look for values in the table, look for values close to 95%, close to 95%. Okay, so we're looking at values at the end. Right, so we'll probably look at this one, and this one. Right, so let's write out what they actually mean. So that 0.8826 goes with the 3, so that's this one here. This one goes with a 4, and this one goes with a 5. Okay, like that. My lines have gone underneath my shading, which isn't great, so let's get rid of that. Okay, right, so the 3, what does that mean? Well, if we read it from the top, that means that the probability that x is less than or equal to 3 is 0.8826. So that means that the probability actually that x is greater than or equal to 4 is 1 minus that. 1 minus 0.8826. So if we work that out, I'll draw over the table. 1 minus 0.8826 is 11.74%. Let's call it that, 11.74%. Okay. What's the next row down? Well, the next row down, it would be the probability that x is less than or equal to 4. And that is 0.9777. Now, what does that mean using the table the other way around, well, that's the probability x is greater than or equal to 5 is 1 minus that. 0.977. Now, what percentage does that give us? 1 minus 0.9777. We get basically 2.23%. 2.23%. So, because we're looking for the probability that's dropping below 5%, this is going to tell us when something's gone wrong. We're interested in this one here. So when we observe something, observe 5 or more in this particular question, we're suspicious. So we would say that the critical value, I know it's not asking for the critical value, but we say the critical value is 5, and the critical region that they're asking for, because we're looking for an increase, is when what we observe is greater than or equal to 5. Part B, state the actual significance. Well, it's not 5%. We actually worked out it was 2.23%. So the actual significance level is 2.23%. It's the actual value that we work out from the table. Okay, a random variable x has a binomial distribution with a sample of 40 and a probability of p. A single observation is used to test. H0 is 25% and H0 is not equal to 25%. So we're only interested in this column of the table. That's the 25% column. And because we're looking for a change in the probability, and we know we're looking for a change because of this not equal to sign here, that means that there could be a change in the probability of something happening when there's been either an increase in what we observe or a decrease in what we observe. That's why it's a two-tailed test. We're looking for at what values of x do we decide something's changed. Yeah, and we're going to find those values. Now it says 2% level of significance, but when we do a two-tailed test, basically that significance level gets split in half and we look at 1% at either end. So let's start by looking for the lower critical value. Okay, the lower critical value. What value of x do I see the probability, now this time not below 1% but as close as possible to 1%. Now let's have a look. It's sort of going on here, isn't it? Yeah, one of those is closer to 1%. Let's see. So that one is 3, this one is 4. So when the probability of what I observe is less than or equal to 3, that is 0.0047. Okay, let me work out how far away that is from 1%, and that value is 0.0053 away from 1%. Let's go up to the next value, less than or equal to 4. That is 0.0160, and I can see that value, so if I do 1% or 1.6% minus 1%, and that value is 0.006 away. So this top one is closer. So my lower critical value, x equals 3, is the critical value. The critical region is when I observe something less than or equal to 3. Now let's look for the upper critical value. This is always the one that's a little bit more tricky. Upper critical value. So this is where we need to be able to interpret the table back to front. Now, if I'm looking for an upper critical value and it's 1%, I'm really looking for values close to 99% at the other end. So there's 99% there. That's a little bit less. So I might try a few of these and see which one I get, which is closest to 1%. Right, so let's try these. Let's start with the 16. So when the probability of x is less than or equal to 16, that gives me a probability of 0.9884. So that means that the probability of x being greater than or equal to 17 is 1 minus that 0.9884. And what I get, so 1 minus 0.9884, I get basically let's write these as percentages, 1.16%, 1.16%, so that's close to 1%. Now, as I go down the table, the percentages are going to get smaller. So I don't go to 15, I now go to 17. X is less than or equal to 17, and that is 0.9953, which is the same as the probability of x greater than or equal to 18, which would be 1 minus that 0.9953. So if I do that, 1 minus 0.9953, and I get basically, whoops, my calculator's gone a bit haywire here. Do this again. Well, I'm just trying to get out of standard form. 0.47%. 0.47%. Now I want to work out which one of those two is closer to 1%. Okay, so the one which is closest to 1% is this one. So if we observe anything greater than 17, we're going to be suspicious. So the critical value is 17. The critical region is when x is greater than 17. Now, depending on which version you have of the book, it may say that the critical value is 18. That's because the table's been read wrong. They've done the probability of 1 minus, or they've read the probability of x less than or equal to 17 as 0.9984, and that's actually the probability of 16. So it's wrong in the book if it says that. So the actual significance level of this test, which is part B, that's going to be the actual probabilities of the critical values that we chose. So that's this probability here, which is 0.47, and this probability here, which is 1.16. So the actual significance level is going to be 0.47% plus 1.16%. And if we add those together, so 0.47 plus 1.16, we get an actual significance level of 1.63%. So 1.63%, okay, which is actually the same answer that's in the book. So there's been a mistake somewhere. Something's not quite right, but the actual significance level I got basically by adding those two percentages together. Right, you should now be able to do exercise 7B on pages 103 to 104 of the textbook.